Okay. And then we've got our time, so we've got NBA. For B, you just put the difference, right? How much the B changes. And then, you know, yeah, I mean, who knows, right? Actually, I think this one ends up being positive because of the other minus. But you know what? It doesn't matter because we always ignore that minus sign. I think it's just one loop. Yeah?
Yeah, it doesn't matter. Does it matter which you
Say it again.
Does it matter which
If we're ignoring the minus sign in general, it doesn't matter. I hate to say that, but it really doesn't matter because
if you include the minus sign, you should compare.
it's always final minus initial. Yeah. So 1 times okay times, let's see, NB is, so we got NB, A is 0.015 squared, right? It's not a lot of volts. Yeah. Are you a skier?
Yeah.
That's another good reason to be in Bozeman. I had a cousin that lived in Bozeman till recently, and he skied till he was like, you know, old or something.
Yeah, Bozeman's
The magnetic field is. I'm confused. I get it.
What does that say? 30 volts. 303. I got you with centimeters, I think. It's 0.015 meters is our radius. 0.03 volts.
0.03 something.
Yeah. It's 0.03 because you squared it. You're off by 10,000. What? Yeah. Yes.
mathematically the same as doing BA cos theta minus BA cos theta.
Yeah. I just factored it. That's right. Yeah, we're going to do that. We're going to argue bitterly about the direction of the current. I get 0.030 when I do it. Are you in radians or? Yeah. There you go. There you go. Yes. Yeah. You have 2 sig figs though, so. Yeah, that's too many sig figs. I'm sorry.
What's like the ACW and the other?
I know. How do you figure out the anti-clockwise? We'll do that. I promise. Yeah.
Wait, ACW, not CW?
It's ACW, baby.
I put CW.
Yeah, you got it. It's still. You what? You hated your physics teacher. Well, you know, the problem is you're comparing your physics teacher to me, you know, which is just unfair. You know.
It's just a really bad teacher.
Could be.
But it was funny because he was teaching an honors course.
Oh, pi r squared is the area of a circle.
You got circle.
Yeah. N delta B, right? Yeah. A over T. Boys and girls, so point your eyes up here if you would. On this problem, right, notice that I just took the B and just subtracted the B. The reason I can do that is that if it's BA cos theta minus BA cos theta, the thing that changes, everything that doesn't change you can factor out, right? So the N factored out, the B didn't factor out, but the area did factor out because it was the same, right? And so that's why you get this expression. It doesn't matter, you can do this, it's just more work, right? Are we okay? Does everybody get 0.03? Okay, let's argue.
What's ACW?
Yeah, let's argue about anti-clockwise versus clockwise, right? Okay, so I think it goes anti-clockwise, and here's why. Okay, this magnet approaches that loop, and this is actually kind of difficult. Let's talk about the motion of the magnet. What do we do? In general, what do we do? The induced current should do what? Should oppose. So how do you oppose the motion of a magnet toward you?
The other way.
You make a magnet that repels the magnet that's approaching you, yes? Okay, so here's gentlemen, here we have a north pole approaching this loop, right? So what does the loop do to oppose that motion? Makes a north pole toward it. So how do you make a north pole toward it? You go this way, right? So however we envision this loop of wire, we know that it's going up the back side, down the front side, yes? Okay, to make a north pole that opposes that one there. Okay, now, why does Lenz's law work that way? Well, think about that. If this is a north pole magnet, isn't there going to be some resistance? As I push on this, I'm doing work. You can see the beads of sweat beading up on me, right? My massive guns are flexing. In fact, I might even like rip my shirt. Are you picturing that? I'm pushing that there. I'm doing all this work. Where does that energy go? It goes either energy is not conserved and it disappears from the universe, or B, goes into the wire, into generating electricity. That is how the energy of falling water at Bonneville, that really was true. I was joking earlier, right? How the energy of falling water to electrical energy. That the motion of the magnet is doing work in the form of energy. Yes? In the form of electrical energy? Ah. So that is why Lenz's law works. It just makes conservation of energy work. If it were the other way, that the current helps the change in flux, it would be this. This is what would happen. Current would flow the other way. This would be a south pole magnet. The magnet would go faster and faster. The current would get bigger and bigger, and it would explode, and the entire universe would disappear into a singularity, right? And so therefore, all universes that had non-conservation of energy laws, right, where Lenz's law was messed up, cease to exist, and we only have universes where it does exist. Right? This could actually be true, but I'm not going to really publish that. Okay, right? You know, so in our universe, right, energy is conserved, and so the work that I do pushing the magnet turns into electrical energy. We could hook a light bulb to this, and it would light up, or we could heat our house or move a motor. Now, okay. Then the other question was, which electrode, A or B, is positive? Well, if the current is flowing anti-clockwise, and if this side is behind this side, right, then it's flowing up that side, down this side, so it therefore flows out of A and would need to flow into B if it were to complete the circuit, right? So A is your positive side, B is your negative side. Okay, and people, we can argue about that. People like lose friendships over that argument. Yeah? As long as it's moving, as soon as it stops, it quits, current stops moving. Yeah. And then the question is, how do we know it's positive? Because it comes out of the positive one, right? So if it's going anti-clockwise, it's going out of this guy and into this guy, right? Current flows out of positive to negative, yeah. Yeah. Okay, let's do another one. Another nutter butter. Okay, let's do the direction of this one first. Okay, here we've got this guy sliding this way, yes? Are you picturing that? So what is changing? Is the magnetic field changing?
No.
No. Is the angle changing? No. Is the area changing? Yes, it is indeed. In fact, we're getting more and more area inside our loop, aren't we? Okay, so let's go to our direction. Okay, we oppose the change. So are we gaining flux or losing flux? We are gaining. We are gaining flux into the page because it's x's. Yes.
Line that's moving with the arrow.
Yeah.
Okay.
It's what's causing it, right? This part stays still. Okay, so we are gaining flux into the page. Yes. So what do we do? What's the recipe for a gain? We oppose it. So how do you oppose into the page? We make flux out of the page. Yeah. How do we make out of the page?
Anti-clockwise.
Anti-clockwise. So there's all these steps where you can make a mistake. Remember, always make an even number of mistakes. So if you make a mistake, go ahead and make another one right away. But then don't then make one more mistake, because then you'll be wrong again, unless it is to then make yet another one and make it 4 mistakes, and then you're right again. Okay? So let's do that again. As this slides, the area inside here becomes bigger and bigger, because this U-shaped thing stays still. This thing slides this way, the area gets bigger. So we are gaining flux because of area. It's into the page because it's x's, right? Gaining flux into the page. If we gain it, we oppose it, so we make flux out of the page. Now, as luck would have it, there's another way to predict